All right, so thanks everyone for coming back from the break. We'll start with our next session. Our next session features talks from two developers of NAMD. Well, Jim, I guess, sort of formerly was. So the next talk is by Jim Phillips, who used to be lead developer of NAMD and now works at NCSA. He's going to be talking about the experience with Charm++ and NAMD on Summit.
Thank you, Ronak. So yes, so my name is Jim Phillips. I am the quality assurance lead for the Blue Waters project office. For those of you who are not already familiar with Blue Waters, welcome to NCSA. This is the largest Cray machine that's ever been built. It has a large number, 22,000 CPU-only nodes, and also a significant number of GPU-accelerated nodes. This is comparable in many ways to the Titan machine, except Titan has GPUs on every node. The application mix on Blue Waters that was pre-selected by the NSF before the architecture of this specific machine was decided on informed that balance between CPU and GPU nodes. It also has a very high-performance file system, various other utilities that make it an excellent machine for highly productive science. But it is getting a little bit long in the tooth. It's just hit its 5th birthday earlier this month. The NSF is working towards a new leadership class machine. This is a call for proposals that came out late last spring, and the proposal was submitted last November. I can't tell you really anything about what we submitted, and the NSF hasn't really told us much about the progress of the selection process. But looking at the call for proposals, you can see that they're looking for not only HPC, but also data analysis. Data analysis includes machine learning type applications. They want a 2 to 3-fold time to solution performance improvement over the 5-year-old machine. And then this will lead to a larger phase 2 system that would be ideally a true leadership class machine at the time. So they want 2 to 3 times faster, but the budget is 1/3, so this was challenging, but it was a great experience to be involved in solving this problem and submitting a solution. The workload on Blue Waters comes from basically every domain of science out there, but you notice the largest chunk is for biophysics. Biophysics including basically molecular simulations and related structural simulations. A lot of the science as well as the software for the biophysics usage on Blue Waters comes from this group across the street, where I was from 1994 until just last spring. So they have the visualization and analysis code VMD and then NAMD, the topic of this talk. Been around for quite a while. We lost one of the founders, Klaus Schulten, co-founder Lax Makant-Kale is, of course, still involved. So this is a very long-running collaboration with the Parallel Programming Lab, long-time users of Charm++ with the NAMD program. And shortly after the passing of Professor Schulten was renewed for another 5 years with a perfect score under the new leadership of Ahmad Tashkhorshid. So NAMD continues on into the future. The driving projects for the next 5 years, the philosophy behind the NIH is that you don't just develop software, you develop software to solve classes of simulations. And the classes of simulations that we've been addressing are really quite varied. So we have large simulations such as the famous HIV and other virus capsids, even larger neuronal processes in the brain, basically understanding how does the brain work at a molecular level? What does the transistor look like? How is it controlled molecularly? Very large bioenergetic membranes, for example, the chromatophore. How the surface membrane of a bacteria actually allows it to sense its environment and respond. So this is what can be thought of the bacterial brain. And really, these large simulations have been driven by, we also have smaller simulations. So these are, for example, molecular motors, membrane transporters. They're not so much large, but they have very long time scales. For example, up to a millisecond, which is a different type of challenge. So the different driving projects have been pushing NAMD towards petascale computing and beyond, basically for the entire history of the program. So we've seen increasingly larger simulations, and this is, when Blue Waters was new, we have somewhat larger simulations still in the works. But this isn't driven because the machines have gotten faster. We're doing this because the science of the biology has gotten larger and more complex. So if you look at these systems, this is not, gratuitously larger. We're not just simulating more and more stars to see more and more galaxies. This is, one lysozyme, one ApoA1, one ATP, one virus capsid, and again, one virus capsid with the HIV, and this is not a symmetric system. Every protein in this HIV capsid is in a slightly different environment. So you can't understand the collective functioning of the entire capsid by only simulating a small part of it. So the tool we use for this is, of course, the NAMD software. This is used not only by the Beckman group, of course, but it is the widest used application on Blue Waters as of the workload study a couple of years ago. Also on the lesser Exceed machines at TAC. We've been pushing the edge of technology to do these simulations for years. So, example, back in 1993, we were already early adopters of workstation clusters running on HP. Then we adopted Linux clusters. And finally, we were basically one of the first groups in the world to use CUDA back in 2007, basically before it was even re-released, thanks to a collaboration locally. And we've continued this by pushing for application readiness and early science projects on the pre-exascale and now exascale class machines of the Department of Energy. So we completed an early science project on Argon Theta recently. Oak Ridge Summit is, of course, in progress now. We just got access to the machine about 2 months ago. And Argon, unlike Oak Ridge, which is making us do a lot of work and run benchmarks and tune our code, Argon decided to procrastinate by a couple of years to get a factor of 5 increase in performance. So in 2021, they extended our early science project, so we will be one of the first codes on the first US exaflop machine. So this is very exciting, and of course this is the legacy of Klaus Schulten and the enduring collaboration with Professor Kalle, for which they received a Fernbach Award. So NAMD is very good at these large simulations. This is going back to basically 2014 at Supercomputing, and then some improvements on the Blue Waters and Titan GPU accelerated XK7 nodes. One small point here, you may ask, if Blue Waters and Titan are sister machines, why is Blue Waters scaling better than Titan? And the answer, of course, is the skill of NCSA, but primarily this is a topology effect. And at least for this data point, even if we didn't have the topology-aware scheduler on Blue Waters that removes a lot of the interference, this is basically all the GPU-accelerated nodes on Blue Waters, whereas on Titan, this can be 4,000 nodes scattered pretty much anywhere across the machine. So we're seeing more or less maximum interference from other jobs on the Taurus on Titan. But nevertheless, good success both for CPU-based and GPU-accelerated machines for very large simulations. For the smaller simulations, such as the membrane transporters, NAMD can also be used to study these millisecond-class processes using intelligent sampling method. So here we have accelerated a large number of small simulations running on a small number of nodes each, but intelligently coupled to produce not only a complete trajectory, but detailed thermodynamic properties of the system at that trajectory. So this lets us use the petascale machines for not only large simulations, but also very advanced simulations of small systems. Of course, NAMD is based on Charm++. It's been based on Charm++ for a very long time, so we have a rather simple method of what Charm++ does for us. It's data-driven objects, asynchronous methods. Prioritization of messages and execution is very important for the efficiency of the algorithm, but not the correctness. And then we also make use on the CPU systems of measurement-based load balancing. We're not using some of the bleeding edge methods because though they may have been inspired by NAMD, NAMD had developed its own specialized solutions at that point. We have a unique decomposition among MD codes. So we decompose the atoms spatially, so into these cubes that are larger than a local cutoff distance, and then the interactions between these different sets of atoms, represented by the pink diamonds, can be independently scheduled across the machine by charm++ load balancing, although there is a communication optimal distribution that is used initially. Charm++ lets us overlap the long-range slow FFT of the electrostatics algorithm, particle mesh AWOLD, with the more local calculations for the bonded and non-bonded terms locally in the force field. And this is performed asynchronously, so we move the atoms, calculate forces, move the atoms again. And when it came time to port to GPU clusters initially, we just took the most intensive part of the workload and offloaded that and kept as much code as possible on the CPU. So in order to scale across nodes, it was very important to overlap the communication between nodes and both between the CPU and the GPU with as much force calculation as possible. So we would do the forces that needed to be communicated off nodes first, send those, get the remote forces back asynchronously, update positions, and loop. And this was way back in 2008 on some of the very early GPU clusters. What we do now is we stream those results. So rather than calculating a block and sending, we can use some tricks with the memory system on the GPU to move individual patches back to the CPU and continue processing them during the simulation. So for example, we have before with the non-streaming kernel, pink line represents running on the GPU. Everything else is what's bound on the CPU. So this is several years ago, but again, we're getting data back, integration happens, continue, data communications, local data continue. With the streaming kernel, we're able to overlap these much more. So the idle time of the GPU drops significantly. We still have significant idle time here, for example, in a PME step. But this was one of the tricks that got us good performance on the Blue Waters and Titan class machines. Moving more recently, this is some work done by Anni-Pekka Heinonen, who unfortunately passed away last summer in a car accident, but he did a lot of work improving the single node GPU performance of NAMD, so between NAMD 211 and 212. We had a significant increase. Coming in the future, some additional work that we got integrated into the code base last spring, offloading not only the non-bonded calculations, but also the lesser bonded calculations to the GPU. So we get a significant speed up, and this is not because this is a lot of work. This is because this is removing that work from the CPU, which was increasingly the bottleneck, particularly on a machine like an NVIDIA DGX-1 that had 8 GPUs for 2 CPU sockets. So where we are now is, of course, looking at Summit. So Summit is designed to have 5 to 10 times the aggregate performance of Titan on a smaller number of nodes, but those nodes are in fact very fat. So instead of 1 Opteron and 1 Kepler, we have 2 22-core Power 9 processors plus 6 NVIDIA Voltas on each node. You can think of this as 2 half nodes with 1 Power 9 and 3 Voltas, and of course you can use it as a set of 6, 7 core processors with 1 Volta processor each, and then it has a dual rail 100 gigabit per second network between the nodes in a fat tree communication. So running NAMD and charm++ on this machine, we're benefiting greatly from the PAMI layer that was developed over many years by IBM, initially by Samir Kumar, and more recently continued by Bill Gayakun, former graduate student at the group. Initially for the Blue Gene series, this is a communication layer that targets IBM's PAMI layer, which is being used on Summit as the basis for IBM's MPI library. And this is unique for shared memory charm++ layers in that it does not require a communication thread. So you can, in theory, use all of the cores for the communication in the process and move forward. there is one, we're running with one GPU per process. That is a restriction of the PME implementation, the scalable PME implementation in NAMD. Plus, it provides some separation and more efficiency in the CUDA libraries that don't deal with multiple devices being called from multiple threads very well. So this basically gives us the maximum bandwidth we can get to the network while still providing as many cores as possible per GPU. We are leaving extra cores free because, as I'll show you, we've had some noise issues on the machine. We could, in theory, get this down to 2 unused cores per node, which are explicitly reserved by the operating system. We are explicitly setting thread affinity. So this JS run command is locking the available cores down already so that you can't use the other sockets GPUs, for example. We are running this, again, 6 processes per thread, explicit sets, although we can also use the default affinity, which allows threads to migrate and may help with noise issues somewhat. If we look at projections, we can see pretty clearly what's going on with the machine now. Even with the entire force calculation offloaded, this is where the GPU is running, is these little pink bits, and this is PME. Red is simply integration, moving the positions forward and applying some constraints, and then everything else is communication activity. White, we see some load imbalance, which is a little unexpected, but basically we can say, okay, if you want to speed the code up, the number one thing you need to do is shrink this integrator because that's all that's left on the CPU. I have not really done anything to optimize the GPU side because it's not the bottleneck at this point. We can overlap this if we can get the integrator down fast enough. So the question is, where's this load imbalance coming from? And it's sort of hard to track down, but Charm++ has a tool in projections called Extrema, which will show you which PEs have different characteristics. In this case, which ones have the least idle time. And then we can say, okay, I want to look at the not idle PEs because we can see this is the average. Something is overloaded, particularly this one has 0 idle time. So we load those PEs and we can in fact see, yep, there is no idle time. So this is really a load imbalance problem. Now, this integration load isn't load balanced by Charm++. So we're not doing any measurement. We can't fix this with the software we have now. So we have to ask, why is that happening? The other thing you notice is that all of the overloaded PEs that are loaded here have the GPU control logic running on them. So that's 256 nodes. If we bump up to 512 and show all the PEs on the process, we can again see this is busy. There's plenty of idle time on the other PEs in the same process. So, well, what happens if we try to remove the patches from those overloaded processors? So now we have a situation where there are no patches on the GPU nodes. So we see here node 0 is a little bit different because we saved some of the first ones, but no patches on the nodes running GPUs. And now we see sort of a better distribution. And this is showing the overloaded patches. And you can see none of the overloaded patches have GPUs. The GPU ones are a little bit faster. And again, we go up to 512 processors, loading everything. And we see, okay, here's sort of the most loaded PE in the system, but it still has some idle time. So this makes the curve look better. What load imbalance there is delayed until the PME steps because that's how Charm++ works. You don't synchronize unnecessarily, but when you do a global operation, these overloaded processors get there later, and the underloaded processors get there first. You distribute your communication a little bit, and you get resynchronized at the end. So we see a similar improvement on 512 nodes, where, again, there are no processors. The overloaded processors still have some idle time. And if we show all the processors, we see the same kind of effect. So zooming in on this, one property that we can notice is that, okay, here's the GPUs, and here's the integrator. Here's the GPU, here's the integrator. So we're really even not seeing overlap between the GPU and the integration code, simply because the overhead of offloading to the GPU and communication activity between nodes is taking most of the time that we would normally overlap with integration. So we can see very clearly from projections where we need to go. Looking at the benchmarks, a couple of notes. This is very early. We've had access to the machine for less than 2 months. They actually just took it away for Gordon Bell testing. They won't accept it over the summer. We've only got 1,000 nodes. They're working on it. There are always problems, and the GPUs are really fast. This is the problem we're ignoring. These traces were from 3 weeks ago. Some testing last night. Things seemed to be somewhat better, but we were seeing processes yanked away for 80 milliseconds for whatever reason, which is not something that you want your supercomputer to do. So the benchmarks I'm showing are basically the lucky segments that didn't involve that. So if we do this comparison for the large benchmarks, you can see Summit is way up ahead of the older machines. So 20 million atoms is up here and here. This red line is 224 million atoms. So again, nice big gap with the other machines. But remember, this is sort of a 1 socket, 1 GPU node. Summit is 2 socket 6. So if we remove, first of all, simple comparison, GPU benefit versus the CPU, again, pretty substantial, but that's a lot of devices being used here. If we slide it over and we sort of count the number of sockets plus GPUs, then the performance increase from the GPUs versus if they had built an all-power 9 machine, it's still there, but it's less than what you would want it to be. And if we look at this across machines, we can now see, okay, per socket, we're doing substantially better than the older machines, but not, a factor of 10 or a factor of 5. So as I showed, there's still work to do. If we play a couple games to try and make the integrator smaller and project what the benchmarks are going to be, we're getting up into the 100 nanosecond per day range projected to the full system for 200 million atoms. Our goal is roughly twice this. And just to wrap up, again, this is really a new era in GPU acceleration, very fat nodes. The CPU is going to be the bottleneck, not just for NAMD, for a lot of codes. Vectorization isn't going to get us there. We really need to offload to the GPU, which is partly what Dave's going to be talking about next. Optimizing the GPU code is not our priority. We're going to do that last because it's not the bottleneck. And I expect the noise issue to be fixed, and some brief acknowledgments. And thank you very much. I'll take any questions.